Okay, good morning. Let me start. This morning we have two presentations for the school. One is should have given by Matteo Meneghesso, but for some personal reason he cannot be here. So I will give the presentation on his behalf. I hope to be able to give a good talk as well. And then later on we have Martin Rittner from Bosch that will speak also about packaging and system at system level a little bit. So this morning, let me start with an issue that has been mentioned yesterday several times in the speech by Eike, but also by Farid. Because this material, the gallium nitride material, is not so much mature and there are many interfaces and so on, we do have many instabilities and reliability problems. So what I'm trying to do today is covering this aspect and give you an overview of what we have learned in the last 3 to 4 years within other projects that we are going to apply also to this InRel-NPower project. But this is just a general overview that you may see different aspects of reliability issues. So this is how I have organized my presentation. After a brief introduction, that will be very brief because we have already seen yesterday a lot of presentation about this. I will show you things that I believe is crucial to understand before going into the detail of all the trapping phenomena and as well as of the reliability. Is the breakdown mechanisms in gallium nitride devices at high bias. Yesterday, a little bit Farid spoke about this because he showed that removing the substrate, you can have a larger breakdown. So we understand that most of the problem came from the leakage through the silicon layer. But I will go back to this to be a little bit more deep on that. And then I have divided my presentation in two sections. The first section is parasitic. So not really reliability problem in the sense that the device is not degrading, but just in the sense that because we have a trapping and detrapping in the device, we have hysteresis. We don't have the device behaving in the way that we would like, because we have this modification of the charge in the device active area. And then I will move to the more strict word of reliability, the one related to real degradation. So when the device really shows permanent degradation, and here I will show you a little bit about the degradation of state because the Schottky gate or the P-GaN or the MIS gate. So I will try to go a little bit through the different gate architectures that today are used in these devices in order to show you a kind of overview. Of course, this cannot be a full presentation covering all the aspects. That would take maybe a full school for that. But I will try to summarize at my best. So you have seen, this is just an introduction slide. You have seen yesterday the reason why the gallium nitride is very good, but this picture was not shown. So to me, it is important to show you, why the gallium nitride is good. If we look at this multiply-axis plot, if we consider, you see the maximum temperature, the high frequency, the noise figure, the high current level, and the high breakdown volts over micron, you see here the three major semiconductors. You have the gallium nitride, you have the gallium arsenide, and you have the silicon. Silicon carbide can be closer to gallium nitride. In some aspect, he is better in terms of high voltages, a little bit lower in terms of amps, but is similar to gallium nitride. You see the big advantages of the gallium nitride in terms of a maximum operating temperature, because the wide band gap, you do have a much less generation recombination. The intrinsic concentration is much lower. We can really go to much higher temperature. So you need much less cooling for this device. So the system is much lighter also because this less cooling needed for the operating of the device. The high breakdown, we have spoken this because yesterday a lot, so we know Peter also speak about this physics behavior, so we know that we may have a very large breakdown in these devices. So you see here that if gallium nitride can sustain 400 volts per micron and silicon is only a 50 volt per micron, you may understand that if I need a 1000 volt device, I need at least a distance between contacts of 2 or 3 micron for gallium nitride, but I need 20 micron for silicon. So you may make device much smaller, and because the very high current density is much less wider. So my device is much more compact. That means we have much less parasitic capacitance. Less parasitic capacitance means that we may go to higher frequency. Then the system, we may have a much smaller inductance. So at the end, it's not the device itself that provides a lot of the advantages, but it is the system related to this device that really show a much compact size. So even yesterday, Peter was speaking about cost. But to my opinion, people are kind of blind. They just look to the price of the chip. But they should look to the price of the system, because maybe the chip can cost 10 times more than the silicon. But if my final system costs 10 times less, I can gain on that. So again, in this situation, I mean, the community is kind of divided, but we should be more careful in analyzing the cost-benefit of gallium nitride with respect to the silicon. Of course, this is the table that we have seen. One little drawback of that we may see in gallium nitride, you see a lot of very good green area here, so very good mobility, high electric field, saturation velocity is very high. A little weak point compared to the silicon carbide of gallium nitride is the thermal conductivity. So we need really to cool down the device in the self-heating case. It's kind of different from able to operate a higher temperature, but the necessity to cool down the device, because at the end, any reliability issues, as we will show you later, are temperature related. So the cooler the device, let's say, the better it is for the reliability, even if we can push higher than the silicon. And this is also another plot that you have seen yesterday. I will be very quick. You see where does the gallium nitride and the silicon carbide, let's say in general, will place. I mean, this is the frequency, and this is the power, okay? So you see that it's not always true that for very high power you really need the silicon carbide, the gallium nitride, because transistor and IGBTs in silicon can cover very high power. I have seen a single IGBT done in a single wafer, 6-inch wafer, just one device, can handle thousands of amps, no problem. And the cost is much less than any other. But of course, this device can operate at very low frequency. If we want to have device or system compact, we need to go to higher frequency. So then we can have lower inductance. If a device has lower capacitance, we can make a much smaller compact device and system. So this is why the wide bandgap devices is operating at a relatively high power, but a relatively high frequency. And GaN is a little bit better than the silicon carbide because it can push to a little bit higher frequency, because they're better properties in terms of mobility of the material itself, okay? And then, okay, I will skip this slide. You have seen the application can be from consumer, data center, automotive, industry. I mean, tomorrow we will see Kai, Jorg, and Kai that will speak about the industrial application. And hopefully we have also CA+T that will speak also about the converter, we will see. Okay, just coming closer to my first part of the introduction, let me just show you something that you have seen. I mean, this is a typical structure of a power gallium nitride HEMTs, and as you can see, apart this, let's say, kind of a standard structure of the gate and different layer we have seen yesterday a lot, we have here the silicon. Let me talk a little bit more about the silicon here. Why silicon? If you look to the history, the first gallium nitride devices has been made or grow on sapphire. So the reason is, why don't we have a GaN on GaN? I mean, gallium nitride, the freestanding substrate, is not available today in a decent size. So we cannot grow to classically like the 6-inch, 8-inch, or 12-inch like the silicon, or like the 6-inch silicon carbide. We cannot grow a lingot that we can cut and make a wafer like this. So for the gallium nitride, the maximum that we can do is something that is a few millimeter by few millimeter, or maybe centimeter if you're lucky. So you cannot do nothing of a real industrial size with this. So we cannot have GaN on GaN. So then we need a substrate. The substrate can be, at the beginning was a sapphire, but sapphire is a substrate that it is non-conductive, specifically for thermal is very bad. So the best compromise was a silicon carbide. So then the first device that have been processed in the past were gallium nitride over silicon carbide. Because the material is pretty similar, the lattice mismatch is very similar, we have a lot of advantage, very good thermal dissipation. So that was the perfect. And today, the gallium nitride device used for RF application are done on silicon carbide. But in that case, we don't have very big device, and they can be more, I mean, the cost is something different when you speak about RF or satellite communication rather than in power devices. So today, most of the things is not done even in silicon carbide for GaN-power, is done on silicon. This has been a great push for the silicon industry also, because today most of the silicon large foundry are on the 8-inch or, of course, 12-inch or even more. So the 6-inch and the 8-inch lines are going to be dismissed. So this fact that we may make gallium nitride over silicon can revitalize all this foundry that has the 6-inch and 8-inch line, that they can process gallium nitride made on silicon wafers, because the process then can be pretty similar with some modification. So we can take this production line and revitalize and work for other maybe 10, 20 years. So the cost of the infrastructure is much less. So this is why today we are speaking about gallium nitride over silicon. But the problem that we have seen yesterday, growing gallium nitride over a substrate that it is not itself, but it is a foreigner substrate, like silicon, for instance, you end up with a lot of dislocation. Yesterday, Elke spoke about that. So all this dislocation are a site of a problem for the crystal, because we believe at the physical level, the crystal should be perfect, like the diamond. But here we have a lot of defectivity. And to be honest, it is a miracle that these devices are working pretty well, even if a substrate very bad like this is more or less done. Of course, the progress in the last year are huge. We are having better and better material. But if you look at the defectivity per centimeter square of these guys, is 1,000 times or even 10,000 times larger than any other semiconductor. So it is still a problem. This is a possible table that shows you the advantages of using as a substrate the silicon carbide or the GaN bulk or the silicon. And if you see here, the silicon carbide is very good as a lattice mismatch. The availability of the price is high, and the thermal conductivity is very low. So these are two green, but one big red. The cost is too high. And the cost is the primary point for the end user, as told by Peter and by Farid yesterday. So this is unusable for the gallium nitride power application. It's good for RF, because in the satellite or in the telecommunication system, the problem is much less, but not here. The GaN bulk is even worse. Here, it should not be even, maybe it should be dark. I don't know why this is white. But then for silicon is relatively good. The mismatch, by the way, is pretty big. It's 17%. This is too much. But then the availability and the price is perfect, and the thermal conductivity is reasonable. So this is the reason why silicon, because this big green here, is one of the best candidates, and because of what I told you, the infrastructure. So this is why we are speaking gallium nitride on silicon. The other things that I have discovered yesterday was not to speak much about is, the breakdown and the specific gate engineering. I mean, we wanted to have a device with a very large breakdown, okay? We want to go 10,000 volts or 2,000 volts, whatever. And if you make your device like this and you plot the electric field along the channel, whenever you have some biasing of your device, let's say high VDS, some VG around 0 if it is normally on, and 0 to the source, you go around this. Here at the gate edge, you see a big peak of the electric field. Okay, then you can raise the voltage of your drain until the peak of the electric field reach the maximum voltage, megavolt per centimeter of the gallium nitride. Can we do better? Yes, we can do better. We can do field plate. This has been done in the past for silicon power device. Okay, no problem. It's nothing of new. But we have to remember that we can do this also in gallium nitride. That if you put a field plate, you spread out your electric field. The area below these two lines should be the same, that the area of the electric field is the potential drop, if we apply the same potential drop. And then you see that we may widen the electric field and lower the peak. So with this and this architecture, you can see in the device 2, 3, 4 feed plate. Just because you make this feed plate, you lower the maximum electric field, you make your field wider, and then you can go much higher voltages because whenever you increase the VD, then you rise up all the blue curve in this case. And if you do 3 or 4 feed plate, you may end up with a much better situation, and you can go very high voltages, okay? In this case, we just are keeping constant the maximum electric field, but you see that without the field plate, we reach the maximum at 100 volts. With 3 field plates, we reach the maximum at 400 volts. So this is the idea. Making the field plate, engineering the gate, lowering the electric field. This is something that has been done a lot in the past. So this is as a general point. Let me also to get a little bit into the breakdown issues, because there are some points that also are extremely important for the following of my talk. It is the breakdown. The breakdown in gallium nitride has been one of the biggest problems we face still today. The main reason for the breakdown is that this is kind of this, okay? The breakdown is abrupt and destructive. This is not the case for the other power device, specifically in silicon, where they do have what they call an avalanche capability. Let's say that I have an application of 600 volts, okay? And I wanted to have my devices in that application. What to do the designer? The designer say, okay, let's design a silicon device who has a breakdown around 650. We just make a little over design. Then if during the application the voltage go at 700 or 800 volts for a short period of time, it is not a problem. Because for a short period of time, your device will go into breakdown. It will be a sustainable breakdown. The device will not break at all unless the period is too long, let's say for some microsecond or millisecond, and then that is fine. If in gallium nitride the situation is this, you cannot over-design a little, you have over-design a big. So for having a device working at 600 volt system, you need to have a device with a breakdown that is 1000 volts or 2000 volts. Because you know that if for any reason during the life the voltage across the device is going close to the breakdown or at the breakdown, the device blow up. So this is the major problem. And today, still today, we don't have available device with a sustainable breakdown. When they go into breakdown, they blow up. The reason is that because we don't have really avalanche today, and the reason is because we have a multi-layer structures, and the GaN is very strong, but what we have below and on top, the silicon below and the passivation on top, have a much less breakdown than the gallium nitride. And the weaker layer will fail for first. So we are not able to see the gallium nitride real avalanche breakdown, because before seeing that, we have the breakdown of the passivation or of the underneath layers. Then we may see kind of hard breakdown or smooth breakdown, but what was there is a nice paper from Joachim Wolf that did at ECS 2013 that really look at different breakdown. And see, here you see what Farid yesterday spoke about. This is for very high voltages. This is your limitation. The breakdowns goes this way, go to the conductive substrate if this is silicon and goes up. So this is the conduction path. If you wanted to increase the breakdown, you have to increase the thickness of this layer. Then we may have a breakdown in the channel, but this you need really the avalanche. This is not very often seen. This is also another interesting point, the punch through. So what is the punch through? I will come back in a minute. And then this is a leakage current that also may happen that you have to take care of. specifically for the passivation, you have a surface leakage that you have to deal with. Punch-through is one of the important problems for gallium nitride. So let's say that I have my device, okay? And this, as has been said yesterday and the day before, these are normally on device. We may speak about normally off, but the situation is not that different. So they are normally on. So what I do, I give negative bias to the gate, and I try to close the channel. So the channel is depleted. And if that is the case, I should not see any conduction current. But if I do my plot, what I see, in fact, for negative gate bias, you see that the current is low, but at a certain time, it started to increase. And in order to close this current, you have to give more and more negative voltage to the gate. What is it happening? This gallium nitride substrate, it is unintentionally doped. So it's grow without any intention to have any doping. But because the nature, maybe Elke spoke yesterday a bit, or he can help us to understand even more, during the grow, you do have some free carrier that came from impurities that enhance the carrier density. So this is not really intrinsic material. It is a little doped. So there is some conduction here. So when I close my channel here, electrons can go down this way. This is what we call punch-through. Electrons pass through the barrier and they can have conduction. How can we solve this problem? We can solve this problem compensating any carrier in the buffer here. And there are two possibilities here. One is carbon and another is iron. So if during the grow I include in my layer here carbon or iron, I just compensate. So the free carrier will be attracted by acceptor or donor, depending which carrier they are. This is an extremely important point for two reasons. First of all, I am introducing, these are deep level traps. Okay, so if I am able to do the process very well, understanding very well how this profile of this doping can be done at which temperature, then I do a perfect compensation. And then my layer became insulating, and then my device can have a very good breakdown. But this is not always the case. If I do not very well grow and not very well introducing of these two elements, I just introduce traps. So not only I am not able to compensate the free carrier, but even I am introducing traps that will provoke the problem of the trapping and the instability I will speak to you about later. So again, there is no way to grow, to make my layers without these guys, carbon or iron, in order to compensate and making this layer isolating. This is fundamentally important for power device, because I am having voltages very large here, 600 to 1000 volts, and at these volts, this punch-through will be there. I wanted to remove that one, I have to compensate. And this is a very critical point that are taking a lot of effort for all the company to solve this problem. Another possibility to avoid the punch-through is making a double heterojunction. So this is the heterojunction that I've been showing you yesterday and the Monday by Peter. You see the GaN barrier, this is the GaN layer, electrons spill over from here. But if I make another layer of AlGaN, so I do a double heterostructure, AlGaN, GaN, and GaN AlGaN, so I put here again a wide bandgap material, then I try to avoid electrons to escape. But again, and this is a simulation, you see single heterostructures or a double heterostructure. Here the electrons at high voltage is going well down to the substrate with the double heterostructure, no electrons in the buffer, so everything is confined in the channel. Again, this, by the way, is true for relatively low voltages, less than 100 volts. If I go to 200, 300, 600 volts, even the double heterostructure does not work properly, and the electron will go there again. So even in the double heterostructure, I need to compensate this layer with carbon on iron. Okay, so I think this I can skip. This is what I showed Farid yesterday, so nothing of new. Okay. So with these two little, let's say, common plate to speak about, let me go to the parasitic. So first I will speak about the parasitic, and then I will go to the reliability. So let me go back again to tell you what should do a device that we want to implement in a power switching converter. It's very easy. Should be a switch that can be on or off. It's not doing any amplification. So forget any basic electronics courses that you have done, nothing of that. It's just a switch. So when the device is off, I want the device to sustain a very large voltages with a zero current. And when the device is on, I want to have the device that drop as much less voltage as possible with the higher current as possible. Okay, no problem. Okay, the problem is there instead, because we can do this device with a very high blocking voltage, is not a problem. Device with a very high current, it can do, but there is a problem in the transition from the off state to the on state, and I will show you later what happens, that provoke the well-known dynamic RDS on. What is that? In principle, this is what happens. So this is my device. I want to switch the device from on to off in a very simple case. So let's say I have a high VDD here. The VGS is off. At this stage, the device is below threshold voltage, no current through the device. So no current, no voltage drop, VDS is at a very high level. Okay, current is zero. Current is zero. Then I turn on my device. The device is on, I should see the current if I, let's say, neglect the voltage drop across the drain, the VDS, I will have a VDD divided by RL. And this is my ideal current level. Sharp increase until I turn off my device. Easy. But what happens in practice? This is what happens. The current goes up not as fast as I expected, but it is going down very slow. This is a real measurement we have done maybe 15 years ago. But if you look at the time scale, this is not an error. This is real. This is second. So this is 0.1 second, 100 millisecond. And this is 20 milliseconds. So the device takes more than 20 milliseconds to reach regime. If I am using this device in a fast switching, let's say a kilohertz, so it switches at 1 millisecond or even at a megahertz, the device, I will find the device at this current level. So I am expecting this current level. Instead, I see this one. So in my output IV plot, I will see a much less current than what is expected. This is what is called current collapse. In practice, this is the case. So this is a device that was not very good, of course, some years ago. And we do what we call a double pulse. This is, if you go in the field of these devices, you will always hear about double pulse measurement. What it is? You take your device and you pulse the gate and drain simultaneously, starting from a condition that we call off condition. So you see the VGS is low, so it is below the threshold voltage, so no current. And we have a high VDS. This we plot to 50, but this can be 100, 600, whatever you want. In this condition, the device is off, and then we turn on immediately. And then we measure the current. And then we change the VDS and VGS, and we see what we have. So here, the first line is what we call the reference line, where the bias point, the initial, is 0, 0. So it means that my VGS is 0, and my VDS is 0. So the device is in a quiet condition. No voltage drop across the terminals, no electric field within the device. The device, we suspect, is in a safe condition. If we do from this plot, then we do the pulsing at the real measurement condition, we end up with these curves. So this is the 0, 0 curves is what we call the reference. Then we change the condition. We have this bias condition at negative VGS, in this case minus 8, at high VDS, in this case 100 volts. It means that we are having the device when there are in what we call it in a steady state. It is in an off condition with a high VG negative and high VD. So we have a high electric field here. So what happens in this area? Electrons somehow are injected in the passivation, in the buffer. They are trapped there. Okay? And when I turn on my device, I go to the on condition. The device, I measure the device after a few microseconds. The electrons are still there, and they keep my device blocked. So I see less current than what I was expected. And this is what we call current collapse. And if I increase the voltage in the quiet bias point, like 600 volts, you see here, -8. So I am having the bias point in this condition at a very high VDS. The trapping is huge. And when I try to turn on my device, I see the device completely collapsed, and I see these curves. So this is really the current collapse. In the next step, this was called dynamic RDS-on, in the sense that this is the RDS-on is the slope of these curves, okay? But dynamically, if I measure in a pulsed condition, I can see this one. So this is the static, this is the dynamic. And you see the large increase. And remember the first speech of Peter. He spoke about we need to reduce as much as possible the on resistance to have much less dissipation. We are going exactly in the opposite condition. We design a device. We have a device with material properties and with the possibility to have a wonderful low on resistance, but because the charge trapping that is not able to let the device to be completely on immediately, I see a much, much worse area on. So this is what we call dynamic RDS-on. In dynamic condition, my RDS-on is much larger than in a static condition. Okay, so these are two important words, current collapse and dynamic RDS-on. Remember, these are extremely important. And all the development in the last, I would say, 10 years have been really to overcome this problem, designing the substrate and so on, and the architecture of the device in order to reduce or eliminate the dynamic RDS-on. The real word is that we did not never eliminate anything. We just push at a higher level, but at a higher voltage level, but we will see. So also to give you a little overview, what are related to this current collapse is when we have a negative gate bias, just let me to sketch here a very easy band diagram, okay? When I have a very negative gate bias, I push up the metal here. So what we see here, there is a large electric field, and then the electrons can be injected within the barrier layer to get in towards the buffer. But if we have traps in this area or at the interface here and there, we may have trapped electron over there. So this is an important point. Moreover, we may have other trapping condition, not only just under the gate, but we have a very high field from gate to drain. Whenever we are in the off state, negative gate bias, high VDS, we have an extremely high electric field. And this induce injection of electrons that may go through the surface, that may get injected in the different area here. So we may have trapping or having any charge storage in any area of the device active area. And this is our point. So we need to understand, in order to avoid or solve the problem of the current collapse, first, where the trapping is. Second, the trapping are due to traps, where the traps are and how they have been made, which is the nature of the traps. How can I understand, should I change my grow condition? Should I change my process condition? What should I do practically in order to remove traps to avoid the charge trapping and so on? So another point, with these double pulse measurements, we have seen before a huge collapse. Let's go back here. If I show you this plot and I ask you, can you imagine where the traps are from this plot? I see current collapse. Okay, I see current collapse. Are these traps where? Are at the surface? Are in the bulk? Are under the gate? Are in the drain? Where are the traps? Are here, in the access region, below here? I cannot have any answer about this. A little better measurement that we can do is not measuring ID versus VDS. but just to do ID or GM versus VGS. Because this kind of plot provides you a much better information. In this case, for instance, for this device, from this plot I cannot understand much, but from here I have a clear indication of what is going on. The current drop or the current collapse is due to a threshold voltage shift with a very low collapse in the transconductance peak. Here, the basic electronics tell me that this problem is related to something happening under the gate. So traps, electrons are trapped under the gate because I don't see huge drop in the transconductance, just a threshold voltage shift. So I am changing the potential under the gate. So this, let's say, helped me to localize the traps. In this, I can tell you in this device what was happening. It was just a lot of trapping just at the interface between the gate and the AlGaN layer. Okay. In this kind of device, instead, we have again a current collapse, but looking the GM versus VGS, or let's say ID versus VGS, we see that no threshold voltage shift at all. So we should not have any traps charged under the gate. But we should see, since we have a drop in the maximum of the transconductance in large VGS, we are having trapping in the access region. So we can try to localize traps now. But unfortunately, we cannot say in which layer they are at the surface, are in the buffer. So, but with some experiment, changing the passivation, doing some really good test structure design, we may understand this. But of course, this takes time. Can we do better? So let's say the double pulse provide you information about there are charge trapping, we have current collapse, maybe we can say they are under the gate or not, but it tells you nothing about where really the traps are, which are the nature of the traps, which is the activation energy of the traps, the cross-section. Because with the two important information, activation of the cross-section, activation of the traps and cross-section, we can really try to understand the nature of those traps. And this is what we have done with developing in our labs this drain current transient technique that is a DLTS, deep level transient spectroscopy. With this, of course, this is a much complicated measurement, it takes much more time, you have a lot of data to elaborate, but provide you much more information. So this is not a technique good for qualification of a process. It is a technique used for the developing of the device. And this is what we have done. So let's say that you pulse your device from this typical point, a negative VGS, high VDS, and then you pulse to what you call the measurement point, from this to this. And during this pulse, you don't just measure what happens here, but you are measuring all the evolution of the current, okay? Let me go back to go to here, and you see a real measurement. So this is, be careful, this is a logarithmic scale. So we are going from microsecond to hundred of second. So this is 8 order of magnitude span. And we see the current evolution. We see we start with the current at a certain level, then we have 1 transient and 2 transient. So in the double pulse measurement, you just measure your current here, or let's say one of this point. Here we are having all the current evolution. And with the current evolution, we see this transient. The transient is related to the physics of the detrapping of electron from traps. So here we know that there are some traps that at this time constant 10 to the minus 4, they are releasing the electrons. And this is the time constant, 10 to the minus 4, 10 to the minus 3. And when the electrons are released, the current partially recover. Then we have traps that are going to go against, because we are having another trapping condition here, or traps that are trapping not electrons but holes, or vice versa. So the trapping of holes instead of electrons. And then we have other traps that are releasing electrons a much longer time scale. This is second, 10 seconds or 100 seconds. So with this plot, we just try to understand important information. We have 3 kinds of traps that are affecting my transient evolution. So my current collapse is not due by a single trap level, but by 3. And they have a time constant that can be 10 to the minus 4, 10 to the 2. Okay, how can we characterize these traps? Okay, first of all, let me tell you another things. That if we change the starting point, instead of starting from the F, we start this black one, we start from the blue or the red. These are the different transients. The blue one is what I just showed you, but we may have different transient conditions. So again, if we change the starting bias point during my measurements, I can really go to probe traps located in a different area. And maybe they are also different traps, because here I have a trap that is giving a lower current and then going up, and this dark as well. So again, changing the starting point, I can monitor different areas of my device, and I can probe different traps. Important point. Second point, I can do, for instance, for one kind of traps, measurement at different temperature. What typically I do, I just make because it's much easier, to identify the time constant of these traps. This is, I can see something between 10 to the minus 4, 10 to the minus 3. But if I do the derivative, so first I do a better fitting, then I do the derivative, I may end up with this plot. And it is much easier for me to identify the time constant of the traps as the peak of this derivative. So that is, in principle, the place where we have the largest slope of this curve. But this is much easier for me to follow this point, and then from this tree, this peak moving as a function of temperature, as well as this peak and this peak, I may plot what we call the Arrhenius plot. I have no time to go into detail for this. I suppose you know about the Arrhenius plot. But plotting the log of the time constant, the peak of this, versus some temperature, whatever, as a function of Q over KT, is just the temperature. I see these lines, and from the slope of this line, I can understand the activation energy, 1.1, 0.91, 0.62, and we can also extrapolate what we call the cross-section at infinite. Again, now we started to have important information. We started to have the signature of the traps. We know their activation energy. We know their cross-section, at least not at the real, at the normal temperature, but at the infinite temperature. Okay, but you understand how many data we have now, because we can do this. We have to do measurement at different temperature. Starting from different point, I can do the same of starting from the different point. What we come out is with a huge number of traps. Now, let's go back. What can I do when I know activation energy and cross-section of a traps? First of all, I need a good database. This is an example of a good job done by one of our PhD students who really went into the literature, okay, took all this paper and took all the data point of the traps, and he built up this map. And then on this map, that are traps characterized not only specifically in devices, but can have been traps characterized in bulk material with several techniques. So nothing to do with the device processing, nothing to do with the device architecture, okay? It is really a map of traps. And as you see, you can see the different activation energy here. And what is interesting is that if we take our devices and we plot here the traps that we have identified, this one, for instance, okay? This, plus the one that we have found starting from the different bias point, we have had this result. We found 6 traps or 7, and you see here our big point, the red, the orange, the green, and so on, within our database. You clearly see that our traps are not just random distributed in this plot. We don't see traps that have a slope completely unmatched with the one who are there. We don't have traps who have this kind of slope. Traps are lying exactly in the same direction, and they have located, and they have some specific activation energy. Then what we do is kind of empirical, but it is very useful. We tell, okay, if my trap E6 is lying here, let's go to see in literature what they did attribute traps who rely on this side, this light blue circle, and so on. And then maybe we found that for the E6, These traps are related to carbon interstitial, gallium antacid, defects, and so on. So this has been our matching. We took our measurements, we matched in our database, and looking to the properties of these traps, that again are traps characterized at the bulk material level, we were able to really determine the kind of the traps that we were probing. And with this, we, for instance, identify traps that were used to carbon, the one that you need to compensate your buffer. I can tell you, 99% of the trapping today in gallium nitride device is related to the carbon that you need to have there, as I told you before, to have a good insulating layer, but it is also a site of trapping. So you see a lot of time a carbon, but also you have a GaN point defect. What was Elke speaking yesterday? Our material is not perfect. There is a lot of defect. We have a gallium vacancy, we have dislocation, whatever. These are sites of trapping. But with this kind of matching, we can tell to our collaborators at the industry, look, you are having a lot of carbon, you are having many interstitial defects, whatever. So they know they have to go back to the material. They go to Yoff and they tell, Gaudenzio told me that your material is garbage. Give me better one. And Yoff provide a much better material, as usual. Okay? So you have just to ask Yoff, and he will give you whatever you need. But by joking apart, let's say that this is what is really a kind of, I just show you what is a typical set of measurement that we have done, and then in order to characterize these traps. Is this the end of the story? Not at all. For instance, this we were having device, so I show you a lot of carbon. Let's say, why don't you use iron? This is the other possibility to compensate. The problem is the same. You use the iron in the buffer, and you have, this is a kind of time constant spectrum, is a kind of a peak related to the traps. The higher the iron compensation that you need to have a better breakdown, the higher the peak, the larger the number of the traps. So the problem is the same, carbon or iron. My opinion is that the industry today prefer the carbon for some reason, for less memory effect and so on. But at the end, you do have this problem. Let me skip this.